Welcome to this explainer. Today, we're diving into how an incredible, almost entirely silent device called a STATCOM saves our increasingly fragile power grid from total collapse. And as we explore how this technology stabilizes the grid, we're going to answer the ultimate question that engineers and energy enthusiasts alike always ask about this device. Does it actually take power from the grid in order to save it, or does it have its own inherent source? Here's our roadmap for today. We'll start with the grid's balancing act, meet the STATCOM, see exactly how it's stabilizing voltage, ask where's the power from, and finish up with why STATCOM wins. All right, Section 1, the grid's balancing act. So think of the power grid like a massive high-speed highway. When electrical demand suddenly spikes, say millions of air conditioners all turning on at the exact same time, the network suffers from severe voltage drops. If the voltage sags too low, the system reaches a mathematical breaking point. This risks a massive cascading failure, potentially leaving millions of us in a total blackout. And, the impacts of this instability are actually pretty severe. We're looking at a poor power factor, dangerous voltage sags, and violent load throw-off effects, which is what happens when large sections of the grid just abruptly disconnect. To stop a system from collapsing under all these pressures, engineers have to instantly inject what is known as reactive power to stabilize the line currents and pull that voltage back to normal. Section 2. Meet the STATCOM. Enter the STATCOM. That stands for Static Synchronous Compensator. The STATCOM is absolutely the undisputed hero of modern flexible AC transmission systems, or FACTS for short. You can really just think of it as a massive, highly intelligent shock absorber. It's connected in shunt, which just means in parallel, to the transmission grid. And its whole job is to regulate voltage by instantly generating or absorbing reactive power to keep the grid perfectly balanced. Now, this device has quite the physical footprint. But unlike older generators, it relies on advanced, heavy-duty semiconductors, specifically insulated gate bipolar transistors, or IGBTs. These little guys can switch on and off thousands of times per second. That allows the STATCOM to instantly control the flow of reactive power without relying on any massive, slow-spinning rotors. Breaking it down, the STATCOM really relies on 4 core components. First up, you've got the voltage source converter, or VSC, which does the heavy lifting of converting DC into AC. Then you have the DC capacitor providing the baseline voltage. Third, the coupling transformer acts as the bridge connecting the device to the massive power grid. And finally, the harmonic filter smooths the whole thing out. These 4 components work together seamlessly to translate DC voltage into perfectly timed AC pulses that stabilize our grid. Moving on to Section 3, how it stabilizes voltage. The working principle here is actually beautifully simple. Step 1, the STATCOM detects a change in the grid voltage. Step 2, it rapidly adjusts its own internal output voltage. And step 3, it reacts. It's literally like a physical push and pull. If the grid voltage sags, the STATCOM pushes its own voltage up to support it. But if there's a massive surge on the grid, it pulls the voltage down by absorbing that excess reactive power. To actually execute this, the STATCOM injects a shunt current that acts like a physical counterweight. By adjusting the voltage drop across the system's inherent resistance, it can perfectly correct any sag in real time. It's essentially fighting the grid's fluctuations with mathematically perfect precision. So here is exactly how that push and pull plays out. When the STATCOM's internal voltage is higher than the grid's voltage, it acts as a generator, supplying capacitive reactive power to prop the grid up. But when its internal voltage drops lower than the grid, it reverses roles entirely, acting like a giant electrical sponge to absorb excess power and calm the grid back down. Section 4. Where's the power from? Okay, this brings us to the big mystery of this explainer. If this machine is doing all this heavy lifting, propping up sagging grids and absorbing massive surges, where is the actual physical energy coming from? Does a device designed to save the grid actually have to drain real power from that very same grid to do its job, or does it have its own inherent source? Well, it turns out the STATCOM doesn't rely heavily on the grid for its brute force. Instead, it relies on its internal DC capacitor. This capacitor acts as an inherent energy storage source to create a continuous, stable baseline voltage, meaning it generates its own reactive heavy lifting completely internally. But, there is a catch. Because those amazing semiconductor switches we talked about earlier aren't perfectly lossless. They do generate heat and lose a tiny bit of energy. To compensate for that, the STATCOM does have to sip a tiny fraction of real AC power from the main grid, just to meet its internal losses and keep its capacitor perfectly charged. So the verdict to our mystery is a really fascinating blend. The STATCOM doesn't drain the grid to save it. It provides its own reactive power internally via the DC capacitor, making it largely self-sufficient. But it absolutely does rely on a tiny, almost microscopic real power lifeline from the grid just to keep its electronic brain and switches running smoothly. And finally, Section 5, Why STATCOM Wins. Before STATCOMs came along, grids relied heavily on static VAR compensators, or SVCs. But honestly, when you compare that older technology directly with the STATCOM, it's not even a fair fight. The STATCOM delivers vastly superior response times, operating in a fraction of a cycle compared to the much slower SVC. It also gives us continuous, seamless control rather than chunky, stepped adjustments, leading to truly excellent compensation accuracy. But the absolute game changer here is how they handle failure. Older SVCs actually lose their ability to support the grid as the grid voltage drops. But amazingly, a STATCOM independently controls its output current. It can pump out its absolute maximum capacitive support no matter how low the grid voltage drops. Even if the grid is quite literally on its knees, the STATCOM is still pushing back with 100% of its strength. So the advantages are just overwhelming. We get lightning-fast responses, a perfectly symmetric ability to lead or lag the grid voltage, and because it's all semiconductors, there are absolutely zero moving parts to break down. This silent box simply sits there, preventing the loss of synchronism even under massive electrical disturbances. It's for sure the undisputed champion of modern power networks. Which leaves us with a pretty critical thought to close out this explainer. As we add more and more unpredictable wind and solar power to our networks, our grids are becoming far more volatile. So, are these invisible digital guardians silently pushing and pulling power in fractions of a second, the only thing standing between us and total darkness? It's a fascinating reality to consider. Thanks for learning with me today.